Okay, so let's start. Very good afternoon, everyone. So it's our week 10, and today we'll be solving problems on the experimental determination of transfer function. We'll also be seeing the effect of zeros on the system response. So this week's assignment is relatively easier for you. So there are two types of questions basically. Type one is that you're given a Bode plot and you're asked to find the transfer function, right? And there are different questions based on that. For example, you're given a transfer function in terms of some unknowns. When you are given a Bode plot, then you'll be asked, okay, find the transfer function. Then you can eventually find those unknowns as well. Second type of questions are based on this effect of zeros on our system response. For example, if we have a non-minimum phase, if we have a minimum phase transfer function, then if we add zeros in the right half, what happens to the response, right? So uh, uh, the number, like the question, these are the type 2 questions which we'll be having in your assignment. So let's start from type 1. Let's solve our question number 1 for today. We're given a Bode plot. We are given a Bode plot, Bode magnitude plot. So this is the transfer function that's given. Right, so this is the transfer function that's given to us, and we have to find, this is the Bode plot that's given to us, and we have to find the transfer function. Right, so you know that when you have like this, you know this thing. First, let's revise. If your transfer function contains a pole or a zero, pole contributes to a slope of minus 20 dB per decade. And a zero contributes to a slope of 20 dBs per decade. So the first task, if you're given a Bode plot, the first task is you have to find the corner frequencies, right? So you can see it's something like this. So the first plot is you have to find the corner frequencies. Corner frequencies are the points in the Bode plot where your slope changes. So we can clearly see we have two corner frequencies here. One is 0.1 and the other one is 10, right? So there are two corner frequencies in our case. One is 0.1 and other one is 10. And at 0.1, we have a positive slope. At 0.1, when we reach 0.1, we have a positive slope. And when we reach 10, then this slope becomes constant. So initially it's something, let's assume it's 20 dB per decade. And then after this, it becomes 0 dB per decade. So it means at this point 10, we have a pole because this pole will give a slope contribution of minus 20 dB per decade. So therefore, then and only we can get 0 dB per decade, right? So our first step is to identify corner frequencies. So in our case here, the corner frequencies are 0.1 and 10. So if you have corner frequencies, then you can directly write the transfer function in a time constant form. So the transfer function will be something like this, k. Then we have to identify the number of zeros and the number of poles that we have. So we see from the Bode plot, we have one pole, which is at 0.1, and we have 1 0 at 0.1 and one pole at 10, because at 0.1, a positive slope contribution is happening. Similarly, when it reaches 10, so the slope becomes 0. It means at 10 there is a pole. That's why this becomes 0, right? So so we have a 0. We have a 0 at 0.1. So I can write it as 1 plus s divided by 0.1. So this is time constant form. Whatever term is below s, so in the denominator of s, that's the corner frequency. So directly you can write like that. So 1 0 at 0.1 and one pole at 10. So that is 1 plus s over 10, right? So this is the transfer function. Directly we can write it like just by looking at the corner frequencies. But the challenge is to find this gain k, right? So how do we find this gain k? So the procedure is, since so this the how to find this gain k, there are different procedures. It depends on the type of the system. For example, if we see this system, because there is no pole at the origin. So there is no pole at the origin. So in that case, my k is given by, for a type 0 system, let me write it, for a type 0 system, my k is this, there is this formula, 20 log of k is equal to magnitude of gj omega in dBs. Right. So for a type 0 system, there is this formula, 20 log of k is equal to magnitude of gj omega in dBs. We know the magnitude, like this is the initial magnitude, like this magnitude in dBs. So initially the magnitude is 0 dBs. This is dBs. So initially the magnitude is 0. It means I get 20 log of k is equal to 0. It means k is 1, right? So we will solve some more problems, then this will be more clear. For the time being, just bear with me. Then what we get, our g of s is equal to 1 into 1 plus s divided by 0.1 divided by 1 plus s divided by 10, right? So this is my time constant form of the transfer function. This is the required transfer function. Or I can also write it in this form. Or I can also write it in this form. G of s is, I'll take this 0.1. Okay, let me make it more simple. I can write it like this. S plus 0.1 divided by 0.1. S plus 10 divided by 10, right? So this will be, if you solve it, it will be But why would you write it like this? So it will be 100 into S into, let me cross check. Okay. Sorry? Your voice is not audible. Can you speak again, like clearly?
It's correct, sir. 100 into S plus 0.1. It's correct, sir.
Is correct?
Yes, sir.
Again, I'll check in a different way. Wait. Yes. Yes, it's correct. Okay. So I'll again, some people have joined late. So I'll again explain this question, then we'll move to other questions. So we have this question, we have this body plot given. So in this week, you are asked questions about the experimental determination of transfer functions. So for example, if you're given a black box and you don't know anything about that, so how would you identify that system? So like this process is called system identification. So how would you identify that? Then this system comes into rescue. So what happens? What we do, we give some input to that system at some frequency and observe the output, then vary the frequency and keep on observing the output. So we get a set of outputs corresponding to different frequencies. Then we plot that. So we plot that, we actually make the body plot. So for example, you give some input voltage to a system and you get some output voltage, and with like there is some input frequency f. So you can compute omega equal to 2 pi f, right? Then you can also compute this 20 log of V naught by Vi, or in output or input. So this is my magnitude and this is my omega. So for different frequencies, I'll get different this output. And accordingly in dBs, I'll get different values. So I plot that, I get a body plot. So from this body plot, I can now easily find this transfer function. So when I have transfer function, I know, okay, this is a type 1 system or a type 2 system or a type 0 system. Then I know many properties of that system, right? So this is the main agenda of this week. You have to identify the transfer function from the body plot. So we took this question number 1, where this body magnet plot is given. So our first step is to identify corner frequencies. Corner frequencies are the points in the body plot where my slope changes, right? So we need to identify this. A simple pole gives a slope contribution of minus 20 dB per decade, and a zero gives a slope contribution of 20 dB per decade, right? So based on this, we saw at 0.1, my slope is changing. So it's changing as 20 dB per decade. It means there's a zero at 0.1. Then we reach 10, and at 10, our slope changes from 20 dB per decade to 0 dB per decade. It means my slope is changing by minus 20 dB, right? So that's why I have a pole at 10. So from this, I can write the transfer function in time constant form directly. 1 plus s over 0.1 divided by 1 plus s over 10, because I have a 0 and a pole, because I have 1 0 and 1 pole. Then the task is to find this value k. We will see, like it's very easy to reach this stage to write the transfer function in time constant form, but it becomes tricky to find the value of k. So the value of k, it varies. So there are different methods. For a type 0 system, we can directly apply this formula: 20 log k equal to magnitude of g omega in dBs at, like, at omega naught, actually the beginning of the Bode plot. So similarly, we'll see questions for type 1 and type 2 systems where we'll use different formulas for this, in order to compute this value of k. Then we computed the value of k, wrote the transfer function in time constant form, and after that, we wrote it in the standard form, right? So now let's see another question number 2 for today. I have a Bode plot that's given as, so it's given like this. So this is 16 dBs. So this is in dBs, you should know. This is 0.1, 0.5. This is 5. So log of omega, because it's a Bode plot. So this slope is minus 20 dB per decade. Similarly, this is 0 dB per decade. This is also minus 20 dB per decade. Okay, so let's solve this problem. So our first task is to identify the corner frequencies. So we have two corner frequencies here where my slope is changing, that is at 0.5. So corner frequencies, one is at 0.5 and the other one is at 5, because you see my slope changes at 0.5, it becomes 0. And then again at 5, it becomes minus 20 dB per decade. But here, unlike the first problem where my initial magnitude was constant, here I have slope changing right from the beginning, right? And I don't know what is the value here. I don't know this value, right? So it means my at 0.1 or 0.001, my slope is minus 20 dB per decade. It means I have a pole at origin, right? Because I know pole gives a contribution of minus 20 dB per decade. If it would have been like this, minus 40, so then it means I have a pole of order 2 at the origin, right? So you should understand this. These things you were also taught in the week 5 or week 6 when we discussed Bode plots, and these things are pretty straightforward. So here, what do we have? I have a pole at origin. So the transfer function, let's assume g of s, it will be something like this. Some constant gain, some gain k, and then I have a pole at origin. Then at 0.5, I have a 0. So at 0.5, here I have a 0, pole, and pole. So how do we write it? 1 plus s divided by 0.5. Similarly, then at 5, I have a pole. Then I will write 1 plus s divided by 5. This is it. So this is the transfer function. But we can say here the system is of type 1. So this is of type 1 because there is one pole at the origin. Now the task is to find the value of k, right? So now initially I wrote k equal to 20 log of k is equal to magnitude of g j omega, but for a type 1 system, for type 1 system, remember this formula, that is 20 log of k minus 20 log of omega naught is equal to magnitude of g j omega in decibels. What is this omega naught? Omega naught is this frequency where it begins, right? It can be 0.1, 0.001, it depends. So, and if it is a type 2 system, then here it will be minus 40. Similarly, if it is type 3 system, minus 60, so on. So we will multiply this 20 log of omega naught by R, let's assume, where R is the type of system, right? So I need not write it because mostly we'll be dealing with type 1 systems or at most type 2 systems, right? So just remember this formula, 20 log of k minus 20 log of omega naught is equal to magnitude of gj omega in dBs, right? At that point, like this magnitude. But again, this magnitude is not given. We need to find this magnitude. So basic uh, 11, 12 maths or basic high school maths I'll use here. So I need to find this, the value of like the coordinates of this point. So I know the coordinates of this point. It is 16 and log of 0.5 because it's a log scale. So I can easily find the coordinates of this point, right? So let's first find the coordinates of that point because this magnitude I will use here. Then I can easily find the value of k because I know omega naught, which is 0.1. I would know this magnitude and I can easily find the value of k. When I know the value of k, I know the value of transfer function, right? So here, how would we find this value? Let's assume the value is y because I know x is 0.1. So y, let's assume it's y. So can I write this? This point is 16 and it like is y minus y naught or like this. Y1 minus y2 divided by x1 minus x2 is equal to m slope, right? So y1 here is 16 minus y2 and x1 is log of 0.5 minus log of 0.1 is equal to minus 20. The slope is minus 20, right? So let me copy this. I hope it's clear. If anybody has any doubt, he or she can ask. So now we can easily solve it. So it will be 16 minus y2 divided by or let's like this is equal to minus 20 into log of 0.5 minus log of 0.1, which is equal to 16 minus y2. When you solve this, you will get 13.97, right? So you simplified this thing, you'll get minus 13.97. Then what you will get y2 as? Y2 will be 29.97. So you got this magnitude. This is what? 29.97, right? Now we can apply this formula. We can apply this formula now. Let's apply this formula. So 20 log of k minus 20 log of omega naught is 0.1 is equal to 29.97 decibels, right? So it will be 20 log of k This will be minus 20. 20 log of 0.1. 0.1 will be 1. So it will be minus 20. Minus minus will be plus. So, or let me write one step. So it will be plus 20 is equal to 29.97. So 20 log of k will be equal to 9.97, or log of k would be equal to 9.97 over 20, which is equal to 0.4985. It implies k is equal to 3.15. So I got k, then I can directly write the transfer function, which is g of s 3.15, 1 plus s by 0.1 divided by 1 plus s by 5, I think. Yeah. Oh, there is s at the origin as well. Right? So anybody has any doubt here, so then I can clear it. Everybody knows how I wrote this k, how I solved this, or you want clarification? Yes, please.
Yes, got sir.
So basically what I did, let me write this step again. Might not be clear for everyone, but yeah, it's basic 0.4985. So this log is actually log to the base 10. Right? So how should I find this value k? It means my k will be, what should I raise this 10 so that, so this 10 raised to the power 4.91, I'll get k. So k will be 10 to the power 0.4985. It means k is 3.15. So it's like this. So you will be having questions in your assignment where either these omegas are unknown or these magnitudes are unknown, like some of these, but you will have adequate information to find these omegas or magnitudes. So basically, you just have to make use of this slope formula. Y2, y1 minus y2, x1 over x2, which is equal to slope. So slope will be given, and accordingly, you'll either get magnitude or these corner frequencies, whatever is missing. So, and then like you can proceed. Right. So in this case, okay, this is the required transfer function in time constant form. Again, you can convert this and write it in the standard form. Now let's do one more question. Then things will be more clear. This time, uh, I would want that you guys to like help me answering. So we are given a Bode plot. We're given a Bode plot. We are given a Bode plot like this, where initial magnitude is then correct. So yeah, this is it. So let me make it. So my initial magnitude is 54 dBs, right? Then this is 0.1, this is 2, this is 5, this is 25, this is 40 dB per decade, minus 40, of course, then minus 60 dB per decade, then minus 40 dB per decade, and minus 60 dB per decade. Of course, this is log of omega. and this is in dBs again. Now you have to find the transfer function. The options are, I'll write the options for you. You start solving, by the time I write options for you. 20 s plus 5 divided by s into s plus 2 into s plus 25. B part is 10 s plus 5 divided by s plus 2 whole square into s plus 25. My option C is 20 s plus 5 divided by s square into s plus 2 into s plus 25. Similarly, my D option is 50 s plus 5 divided by s square s plus 2 s plus 25. Yeah, please solve it. Just first find the coordinate frequencies, then find the order of system, write this transfer function in time constant form, find the value of k, because the initial magnitude is given this time. You need not find anything. So initial magnitude is given, find the value of k, then write the transfer function in standard form, because the options are in standard form, not in time constant form. To make it easier for you, corner frequencies. So I have a corner frequency at 2, which is a corner frequency at 2, which is a pole. Corner frequency at 5, which is a 0. Corner frequency at 25, which is a 4. They're all simple first order poles. Based on this, we can write the transfer function in time constant form like this. Why I wrote s square here? Because we see initially the slope is minus 40 dB per decade. It means there is a pole of order 2 at the origin. So that's why then we have a type 2 system. So we have a type 2 system. Anybody? Okay, Ramya has said D option. What is D option? This. Anybody else got D option? Anybody else got D option? Can you confirm what's the value of K in time constant form? What's the value of k in time constant form? Cool, 5.011, so that's roughly equal to 5. Yes. So that's the correct answer.
Is option D?
Anybody else who has got option D?
Yes, I have got option D.
Okay, that's good. So option D is actually the correct answer. So let me give the complete solution. Not everybody has solved it, but again, it's very simple. First step is to find the corner frequencies. Then you have to identify whether these corner frequencies are poles or zeros. So once identified, you can easily write the time constant transfer function. And after that, find the value of k. And the value of k depends on the odd type of system. So here the type is 2. So I told you for a type 2 system, 20 log of k minus 40 log of omega naught, which is 0.1 here, is equal to the magnitude of this, which is 54 dB. So the question becomes easy. Why? Because already this initial magnitude, it's given. So then this 20 log of k, it will be 40. 40 will go here, so it will be 14 dBs. Then log of k will be 14 over 20. That will be 0.7. And k will be 5.01, which is roughly equal to 5. Then the transfer function will be g of s 5 over 1 plus s over 5 divided by s square 1 plus s by 2 into 1 plus s by 25. Correct? But you will see none of the options is this answer. So what you have to write, you have to write the transfer function in standard form, right? So in that case, just take common here. So you'll take 5 common and there here 2 common and 25 common, or there are other ways to write it, just do LCM and all. And finally, you'll get the transfer function as g of s 50 s plus 5 divided by s square s plus 2 to s plus 25. So anybody has any doubt, then I can clear it. Otherwise, we'll move and solve the next problem. Please reach out if you have any doubt. This week, the assignment for this week is relatively easier. So it won't take you much time. Let's solve one more problem so that you'll get your confidence. So the body part is given like this. So this is minus 20 dB per decade minus sorry, minus 40 dB per decade. Let's solve this question. You're not given this initial magnitude, right? But you are given this. This is 14 dBs, right? So this is, this corner frequency is 4. This corner frequency is 1. right? And this is minus 60 dB per decade. There's one more point which is given, which is minus 10 dB per decade, minus 10 dB. So yeah, find the transfer function. Find the transfer function.
Sir, corner frequency at
Mhm.
origin is not given.
1. Oh, yes. You can take it 0.1. No problem.
Okay.
Yes. Again, this corner frequency at origin, it depends, like what are the other frequencies given. So if your frequencies are 0.5 or 0.23, then you can take at origin as 0.001, right? So again, it depends, but you can still, for this case, you can take 0.1 because these are all approximate and asymptotic Fourier plots. So corner frequencies are 1 and 4. So the this transfer function g of s, both are poles. So transfer function will be k divided by, there's also a pole at origin, s into 1 plus s by 1 into 1 plus s by 4. So this is the general form. Then it's a type 1 system. You need to find the value of k. Please go ahead and tell me the answer. Tell me the value of k both for time constant form as well as for general form, standard form. Somebody has wrote the answer. Wait. Oh, 5 points. Okay.
Sir, K is 6.
Okay, 6. Okay. Anybody else got 6? Ramya again got the same answer, and Ramya is actually correct. K should be 5.011. That's roughly equal to 5. Yes, Naveen is also correct. K should be 5.011. And the magnitude is 34 dBs. That's also correct. So it should be 34 dBs. So can you check it? Where were you doing wrong? Like, why did you get 6? Okay, let me solve it. So most of people have done it, but again, for the sake of completeness, let me do it. So we are given the magnitude at this point, and we need to find the magnitude at this point. I know the corner frequency here. I know the value of this frequency here. So I can easily find it like this. So 14 minus y divided by log of 1 minus log of 0.1 is equal to minus 20. Right? So this log of 1 is 0, log of 0.1 is minus 1, this is plus 1. So you'll get 14 minus y is equal to minus 20 or y is equal to 34. So you got y as 34 dBs. So it means this point, the magnitude is 34. Correct? So now you know this is a type 1 system because it has one pole at origin. So for a type 1 system, I know this formula, 20 log of k minus 20 log of 0.1 is equal to magnitude, which is equal to 34. So if you solve it, you'll get 20 log of k is equal to 14 log of k as 0.7, k as 5.01, which is equal to 5, right? Then you can write the transfer function as g of s is equal to 5 divided by s into 1 plus s into 1 plus s by 4. Or if you solve it or convert it into standard form, what you will get, you just have to take this 4 out. So you'll get or g of s, it will be, then this 4, it will go up, it will be multiplied with 5. So it will be 20 divided by s into s plus 1 into s plus 4. So anybody has any doubt how I got this 20, or it's fine? I just solve it. Just do cross multiplication or whatever, take LCM. Right? So any doubt? Any doubt here in this
No,
question?
sir. No, sir.
Okay, great. Now let's do one practice assignment problem. This was asked. So you'll be given a question something like this. For example, you're given a body plot. You're given a body plot. This is a bit interesting, but again, very easy. You're given a body plot where you start with, for example, let me go ahead. So initially your magnitude, this is 0 dBs. So your initial magnitude is something like this. Then something like this. Then it's something like this. And something like this. Okay, so this is the transfer function. This is the Bode plot that's given, and here it's 20 dBs. The slope is 0, you know this. And this value, so now you have to figure it out yourself. This is minus 20. So this value is 0.1. This is 0.001. This value is 1. And this value is 100. Right? So you're given this Fourier magnitude plot, and you are asked that and you're given again, the transfer function is g of s, h of s is equal to k s plus a raised to the power m then s plus b raised to the power n s plus c. So you are given the transfer function as this form. Then find a, b, c, m, n, and k. Yeah, please solve it. Nowhere you are given that whether it's 20 dB, 40 dB, but you have to figure it out yourself. But I again give you one hint. Not one hint, but this is minus 60. So first, we will identify corner frequencies. Can you first tell me what is the order of this system? Anyone?
Order is
Zero,
second order system.
No, it's a zero order system.
zero,
No, order is zero. So order is given by this initial slope.
Order is
Order is
zero or
given
type
by,
is zero, sir.
sorry. Yeah, type. So it's a type zero system. Order we cannot say as of now because it's unknown.
type zero,
We'll
type
find
zero.
it later. So it's a type zero system. And when we solve it later on, we'll find it's a type 3 system. Sorry, order 3 system, third order system. But as of now, the type is it's a type 0 system. Why? Because the initial slope is constant. Right. Okay. So it's a type 0 system. Type 0 system. So what is the value of k? The value of k
10.
is 20 log of k
10, 10.
is equal to 20. Okay, great. This and this goes. Log of k is 1, so it means k is 10. Done. So we're done. We found the value of k to be 10. So now we need to find the transfer function in time constant form. So for that, we need to identify the corner frequencies. So what are the corner frequencies? Corner frequencies.
0.1, 1
Yeah, point
and 100.
1 and 100. So can you tell me what is at point 1? Is it a pole or a zero?
It is a
Sorry, you're not audible.
pole.
Okay, it's a pole, and at 1,
1 is 0.
1 is 0, and at 100.
Again pole.
Can you also confirm the order at 0.1?
At 0.1, order is
Yeah, what is the order of this pole? Is it a first order pole or a second order pole? Like, what is the slope? The slope, can you check what is the slope?
20 minus 20
It is
dB.
second order pole.
Yeah,
First
it's a
order
second
pole.
order pole. It's a second order pole. Why?
Minus 74.
Because, yeah,
Minus
let me see. See, there is one decade. See, from 0.1, we are going from 0.1 to 1, then we are going from 1 to 100. So it's typically drawn on a, like if we draw it on a Bode plot. So I'm giving the decade. So first from 0.1 to 1 decade, what is this change in slope? We are going from 20 to minus 20. So from 20 to 0, it means 20 dB. Then from 0 to minus 20, again 20 dB. So it means there is 40 dB. So this is minus
Yes,
40 dB.
It is a second order. Yes.
So it's a second order pulse, right? So the 0.1
Yes.
is second order. Then come at 1. From 1 to 100, there is again 1 decade. There's
So it is
again,
again second order 0.
yes, it's again second order 0, right?
Yes.
So now can we write the transfer function? Actually, it was given. So now let's write g of s, h of s as k is given as k we found as 10. Then we have to write it as, let's first write it in time constant form. then we will come to the standard form. So it
1
will be
plus
1 plus s divided by 1 raised to the power 2, because
2.
it's a second order, right? Divided by 1 plus s divided by 0.1 raised to the power
2.
and sorry, then what will be 1 plus s divided by 100.
100.
Okay, Ramya probably has solved it and got the answers. A is 1. So Ramya has found out A1. B is 1 divided by 0.1. Okay. Okay, C is, it's 1 by 100 or no? Actually, A will be 1, B will be 0.1, C will be 100. Yeah, C will be 100. Okay, fine. Now let's solve it for others. So we have got the transfer function and we have got some values. But again, we cannot comment as of now because this transfer function is in time constant form and this transfer function is in standard form. So we need to convert it into standard form, right? Again, these powers will not change. So when we convert it into standard form, what we will get? G of s into h of s, 10 into s plus 1 square. No need in, and it will be 1 plus 0.1 square, then s plus 100. Actually, whatever I take common, then that gets cancelled, and again I'm left with 10. Right? So this is the required transfer function that I got. So I can now find this value is 2. Again, this value. So every value I have found. So we can compare the values, right? So we have A equal to 1, B equal to 0.1, C equal to 100, M equal to 2, N equal to 2, and K equal to 10. Anybody has any doubt in this question? Okay,
No doubt.
so yeah, basically that's all for these type of questions. You should now be able to solve these questions. If you are given any body plot to find the transfer function, you should now be able to solve. Now let's come to the type 2 questions, which is the effect of zeros on system response. So now let's consider this question. We are given, consider a closed loop transfer function y of s over r of s is given as s minus 1 whole cube divided by s raised to the power 4 plus 6s cube plus 11s square plus 6s. Okay, so first question is, can you tell me whether this is a minimum phase or a non-minimum phase transfer function? Like whether this system is minimum phase or a non-minimum phase.
Non-minimum,
Why?
because there is a 0 lies on the right hand side.
So what is the definition of a minimum phase transfer function?
All zeros must be lie on the left hand side.
Not only zeros, but poles as well.
Yes, pole as well must lie on the left hand side for the
Right.
minimum.
So for a minimum phase transfer function, the poles as well as the zeros should lie. Yeah.
On the left hand side of this plane.
Yes, on the left top side of the S plane. So, but we can see there are poles, 3 poles, which lie on the right half plane. So no need to check for the poles of the for the poles but we can definitely see the zeros are lying on the right half. It means it's a non-minimum phase system, right? So you might be asked questions based on this. Given a transfer function, find whether this is minimum phase or a non-minimum phase system. So you should be able to answer. Now, second type of questions, if you see, yes, please.
If zeros are on the left hand side, but poles are on the right hand side, then
Still non-minimum phase.
okay.
For a
Either
minimum phase, both poles and zeros should be on the left half.
left hand side, yes.
Now, if your poles are in the left half, but zeros are in the right half, then what happens to the response? So we know stability is due to the poles, right? So let's assume we have this transfer function where all my poles are in the right half. So I know my system is stable. It's not a non-minimum phase system, but I know it's not a minimum phase system, but I know this system is stable. Why? Because my poles are lying in the left half. If you see, there are 4 poles that are 0, 1, 2, and 3, like minus 1, -2, -3, and 0. So this is sort of like, again, the poles are lying in the left half plane, so it means my system is stable. So for such systems where we have poles in the left half plane, what is the effect of a right half zero? That we will see. So if you have gone through the lectures, there was given this paper, this research paper. This was given in the references, so which Professor Ramakrishna has referred to while he taught the effect of these zeros. So this is actually a very interesting paper. You all should go through this once, right? Non-minimum phase zeros. So these are the authors. It's a IEEE Control Systems magazine. This paper. So they see this thing. There are many good like effects which we are seeing. For example, you have read a bounded input, bounded output stability. If you are given a bounded input, you get a bounded output for a stable system. But for an unbounded input, your output should also be unbounded. But here in this case, if you have a pole in the right half plane, for the system which has if you have a zero in the right half plane for a system which has otherwise poles in the left half, then what happens? If you can see this figure number 1, which is showing bounded response of a non-minimum phase system to an unbounded input, the response of the transfer function. So the transfer function is g of s minus 1 divided by s plus 1 whole square. So the poles are in the left half, but there is a zero in the right half. So what happens? What the effect of this zero is that the response becomes bounded for an unbounded signal, right? So you are given we have given e of t input to this system, and then this is the output. So the output is bounded, right? So this is one property. Other property is this. If you see figure 2, the system is g of s minus s minus 1 divided by s plus 1 whole square. So this is the system. So then what we are doing for the system this, which has one positive zero, we can see the step response. So we are giving a unit step to it, and the step response initially moves in the wrong direction. Although the operator might be tempted to abandon the control strategy, the system eventually reverses the course and reaches the desired state. So in this case, patience is a virtue. So actually, the response should have been something like this, right? So if there would have been no zero in the right half, the response should have been like this. But what is happening here? The response initially goes in the wrong direction and reaches this point, then reverses its direction, then comes into the right direction. So this is what is the effect of zeros, right? Adding zeros in the right half. So now see one thing. If you can see the screen, so it started from 0, then went down in the wrong direction, then again here it crossed this zero, right? So this is called zero crossing. This is called zero crossing. So when you add when you add a zero, a positive zero in a non-minimum phase transfer function or in a minimum phase transfer function, then what happens? The response, the step response initially goes in the wrong direction. Then it reverses direction and comes into the right direction. So it basically has the zero crossing, right? Now let's go another figure. Let's say this figure. So the system here is g of s minus 1 whole square divided by s plus 1 whole cube, right? Try to understand this. See, again, initially the system started with correct direction, then it reverses its direction, goes into the wrong direction, again reverses its direction and comes into the right direction, right? But you can see the poles are in the left half, so it means my system is stable. But I am adding two zeros. I am adding two zeros in the right half plane. And by adding two zeros in the right half plane, I can see there are two zero crossings. One zero crossing is at here, another zero crossing is at here. Right? So my system actually crosses zero, goes into the wrong direction, then again reverses its direction, crosses zero, and comes into the correct direction. So you can see the zero occurs somewhere near this, then again the zero occurs somewhere near this point, right? So how many zeros are in the right half? Two zeros are in the right half. And how many zero crossings are there? Two zero crossings are there. Correct? Now let's move to another figure. Let's come to this. So here, again, this is the step response, but the transfer function is g of s 2s square minus s plus 1 divided by s plus 1 whole cube. Correct? So here again, you can see, no, this is actually, yeah, this is something else. This here, they are not studying the zero crossings, they're studying some other behavior. So what I would actually recommend you is to go through this paper. This is a very interesting paper. It studies the effect of adding zeros to a system which has poles in the left half, which is actually a stable system. But when we add zeros in the right half plane, so it becomes non-minimum phase. And the effect is you have some sort of undershoots, like your system either goes right direction, then reverse goes in the wrong, comes back in the right direction, or goes in the wrong direction and reverses, comes into the right direction. But the main point is it has zero crossings. So the main point is it has zero crossings. These zero crossings, they are given by the number of these zero crossings, they are given by the number of poles in the right half. So here I have two poles in the right half, so I have two zero crossings. If I would have three poles in the right half, I would have three zero crossings. So in that case, the system will be something like this. So if it is zero, so it will be something like this, right? So I have one zero crossing, two zero crossing, and three zero crossing, right? So the number of zeros in the right half plane gives me the number of zero crossings, right? And again, the time, we can also find this time where the zero crossings occur, that we will see. So let's come back to the question. So for this system, when a step input is applied, for this system, when a step input is applied, can you tell me how many zero crossings occur? How many zero crossings occur? Can you tell me? Anyone? Okay. So Ramya has said 3. Actually, yes. Why? Because there are 3 poles in the right half plane. The system has zeros, has 3 zeros in the right half plane. So it means there are 3 zero crossings. So 3 zero crossings can occur. Right? So there are some questions where you'll be given some response, for example, like this. This is, let's assume 0, and this is that because you're tracking a step input. So let's assume you are given some system like this, and you're asked, okay, what are the number of zeros in the like tell me the number of zeros in the right half plane for the system. So what is the answer?
1.
1, because there is 1 zero crossing. Right? Similarly, if I make a different graph like this,
2.
right? So 2 zero crossings. So there will be 2 poles in the right. I don't care what is the value of that pole, but yeah, at least there are 2 poles in the right half plane. Right? So similarly, when there are 3 poles, so the figure will be something like this. Right? So there will be 1 zero crossing here, second zero crossing here, third zero crossing here. So you have questions where you're asked about these zero crossings. Right?
Sir, in
Now
this
there
case,
is,
the initial direction is wrong.
yeah, it depends. See, let's make it one by one. So your end point is you have to reach this because it's unit step. You have to reach this. So in case of 1 0, your 1 0 crossing, you will have something like this, right? So initial direction is wrong. Initial direction is wrong, but then it reverses and comes into the correct direction, right? Or let me make it in a more better way because I think you have questions on this as well, where the initial direction is right or not. So for this question, I'll write 3 zero crossings. So let me make the case of 3 zero crossing first. So 3 zero crossing will be something like this. Right? So initially, my system is moving in the right direction. Then it reverses, goes in the wrong direction. Then again reverses, goes in the right direction. Correct?
So what
Any
is, sir,
doubt here? Yes.
initially it exhibit
Initially,
correct,
yes, it's correct. This is the correct way because it has to go here, right?
but direction reverse, no, sir.
Yes, here, look, it starts from here, right?
Yes.
So initially it's going in the correct direction, then it reverses. Here it reverses, so then it reverses, then goes in the wrong direction, then again it reverses, goes in the right direction. So initially it's correct, but then it's wrong. Now see the other case. See the other case. So for example, let's assume I have this case. So this is initially wrong. Initially this is wrong because this is a case of 1 0 crossing. So this was 3 0 crossing. This is 1 0 crossing. So initially it starts from initially the direction is wrong, then it reverses and the direction is right. Right? Similarly, for this case, initially it's correct, then reverses wrong, again reverses right. Right? It's given in detail. If you see this paper, I'll show you. See, the step response of a system with 2 positive 0 initially moves in the correct direction, reverses the course to move in the wrong direction, and then reverses the course yet again to move in the correct direction. So initially it moves in the correct direction. So initially for a system with 2 positive zeros, initially correct, then wrong, then again correct. Now see here. Initially correct, then moves, goes in the wrong direction, then again moves, goes in the right direction. This is for 2 0 crossing, the same case. Is it now clear?
Yes, sir.
Okay. So this is these type of questions are asked in your assignment. Now see another question. The question is, what is the time at which first zero crossing occur? So for this system, we know there are 3 zero crossings. We know there are 3 zero crossings, right? But now we need to find out the time when this first zero crossing happens. Like this time, we need to find out this time. Or eventually, sometimes you might be asked to find the second time, the zero crossing when the time when the second zero crossing occur, or the time when the third zero crossing occur. Eventually, you should be able to find all this. So how to solve such questions? See, again, you are given a transfer function y over s, ys over rs, which is given by s minus 1 whole cube divided by s4 plus 6s cube plus 11s square plus 6s. Right, you are given this. If I open this s minus 1 whole cube, like if I open this, I can write it as s cube minus 3s square plus 3s minus 1. So simple a cube minus 3a square b plus 3a square b, ab square minus b cube, right? So similarly, I just write denominator in this way, s into s plus 1 into s plus 2 into s plus 3. You can easily find the roots because it's simple here. You at least know 0 is the root because everything has s. Then just put values, use cubic. There are many ways you can do this. So I wrote this y over s into r over s, ys over over rs like this. Now see, this r of s is unit step. It means r of s is 1 over s. So or I can write y of s is this into r of s, right? So it implies my y of s is equal to s cube minus 3s square plus 3s minus 1 divided by s square into s plus 1 into s plus 2 into s plus 3, right? So basically now, if you look at the question is what is the time at which the first zero crossing occurs? So we are in Laplace domain. We are in S domain right now, but we are being asked about the time. So we are being asked about t. So we should find yt, right? So when we find yt, then we will put y of 0, like we will find the value of t when this y of t is 0. So that will give us the value of this, that will give us those required zero crossings, like when this zero crossings occur, right? So how we will find this y of t? So this is in Laplace domain. We'll find inverse Laplace, right? So we take yt and inverse Laplace, I will use partial fractions, right? So partial fractions, I'll write this. So first I'll write partial fraction. So it will be s cube minus 3s square plus 3s minus 1 divided by s square into s plus 1 into s plus 2 into s plus 3 which will equal to A divided by S plus B divided by S squared plus C divided by S plus 1 plus D divided by S plus 2 plus E divided by S plus 3. Is it correct? Then again, you'll just like apply the basic procedure, just multiply this with this, or there are many ways, right? And when you solve this using partial fractions, it's not that difficult. Just just put S equal to 0, then S plus 1 equal to 0, S plus 2 equal to 0, S plus 3 equal to 0, and again you'll get the values of A, B, C, D, and E. And finally, what you will get, this Y of S, you will get it as 29 by 36 S minus 1 by 6 S square minus 4 divided by S plus 1 plus 27 by 4 into S plus 2 minus 32 divided by 9 into S plus 3. It's not difficult, right? So then easily, if you take the inverse Laplace, so what you will get? You will get 29 by 36. So you have 29 over 36 minus 1 over t minus 4 e raised to the power minus t plus 27 by 4 e raised to the power minus 2t minus 32 over 9 e raised to the power minus 3t. Right? So this is the expression for yt. Then what you'll do? You have to find zero crossing. So you have to find the value when yt is equal to 0, right? So it's very difficult to solve this equation. So you'll use MATLAB or some other tools to solve this equation. And eventually you'll get t as 0.4578. It's a cubic equation in t. 1 point, like you'll get three values, 1.7276 and 4.5950. So obviously the first zero crossing occurs at this time. So one way is to do this, or simply what you can do, this is an equation for you. Just plot it. So this is one variable y, and the other variable is t or x or y, whatever it is. So you just plot it in MATLAB for some time. Let's assume you chose time as 0 to 10. So you'll get some curve, right? Something like this. So from the plot as well, you can just identify zero crossings. So this is general. It's not like the case like 1, 2, 3. Yeah. So this is a case of 3 zero crossings in this case. So you'll get something like this. So there are 3 zero crossings. You can easily find out the time when these zero crossings occur. But the basic point is you should be able to find the approach. The approach is, okay, you're asked about y of t. So you'll first find the this y of s, take the inverse Laplace, find y of t, and then just see when this y goes to 0, find the value of t. And sometimes if you're asked to find the steady state value, so you know steady state value is the final value or the value at infinity, right? So steady state, if you are asked to find the steady state output to the unit step, so again, you'll find just put t equals to infinity in this expression, and you'll get the answer. So these are the types of questions. First type of question is that from the Bode plot, find the transfer function. The other type of questions are whether the system is minimum phase or non-minimum phase. And other type is what is the effect of zeros, the right half zeros and the right half zeros which are in the right half plane. There are many other properties as well when these zeros are being added in the right half that they are given in that paper. So do check that. I'll just write the title of that paper here. So the title is, wait. Yes, the title is non-minimum phase zeros, much to do about nothing. If anybody does not have access to IEEE, so I can then provide in the comment section right now. So authors are J.B. Fogg, D.S. Bernstein. This is IEEE Control Systems magazine.
Sir, I do not have IEEE.
Okay, just give me a moment. Right. So should be able to, how should I send it? Should I send it? You just ping me on my number or on my email. I'm just giving my email. I'll send it. I'll send it on the email. I'm just writing my email here. LONEJAF03 @gmail.com. So whoever has not access, just email me here. I'll send it. Right. So this was it. Very simple week. So anybody has any questions? Otherwise, we'll just stop the meeting. Thank you very much for attending.